Hey there, future scientists. I am Atom. Get ready to embark on a journey with me where we are set to unravel the captivating universe of the physics of work. Have you ever thought about the effort we put into tackling those textbooks, or navigating the challenges of homework, or immersing ourselves in study sessions for tests? Well, buckle up, because today we are about to explore the true essence of doing work in physics. Work in physics is not about wrestling with science questions or math problems or English essays. In physics, work is done when a force applied on an object, for example, a grocery cart, moves the object in the direction it is being pushed. Work equals force multiplied by displacement. If we lift a small apple of mass 100 grams through a distance of 1 meter, are we doing work? If so, how much? Mass of apple in kilogram will be equal to 0.1 kilogram. Force applied to lift a 0.1 kilogram mass apple would be equal to 1 Newton, since every 1 kilogram mass is pulled by Earth by a 10 Newton force. So, work done on the apple equals force multiplied by displacement, which equals 1 Newton times 1 meter, that is equal to 1 Newton meter. Now, 1 Newton meter is equal to 1 joule. The unit joule is in honor of the English physicist James Prescott Joule, 1818 through 1889, whose work laid the foundation for the modern understanding of the relationship between heat, energy, and mechanical work. So, 1 joule equals lifting a 1 Newton apple through a distance of 1 meter. This time, we are in an airport dragging a suitcase at an angle. How do we compute the work done on the suitcase? The force is not being applied exactly in the direction in which the suitcase is being displaced. In this case, we need to include the angle between the applied force and the displacement of the suitcase into the formula. The complete formula for work done on an object looks like this. Work equals force multiplied by displacement multiplied by cosine theta. So W equals F times delta D times cosine theta. Here is what each component means. W is the work done in joules. F is the magnitude of the force applied in newtons. Delta D is the magnitude of the displacement in meters. And theta is the angle between the force applied and the direction of the displacement. The cosine theta term is crucial because it accounts for the component of the force that is acting in the direction of the displacement. If the force is applied directly in the direction of motion, that is theta equals 0, then cos 0 is equal to 1, and the full force contributes to the work. Then the formula can be written as work equals force multiplied by displacement, or W equals F times delta D. Positive work. In all these cases discussed so far, positive work is being done on the object. Positive work occurs when the force applied to an object aids the object in the direction it is moving. For example, when we lift an apple against gravity, the force we apply is upward and the displacement is also upward. As a result, the work done is positive, and we have added energy to the apple. Positive work also corresponds to situations where an external force causes an object like the grocery cart or the suitcase to accelerate or maintain a constant velocity. So positive work means energy is added to the system. Zero work. When we flex our muscles by lifting a hefty grocery bag, we are not actually doing any work on the bag. Why is it so? So, in this scenario, we see people carrying boxes and walking. If the force is applied perpendicular to the direction of motion, theta becomes 90 degrees and cosine 90 is 0, so 0 joules of work is done on the boxes. Though work is being done on one's muscles since the muscles are twitching in the same direction as the applied force. Negative work. Work is considered negative when the component of the force applied to an object and the direction of the displacement of the object are in opposite directions. This means that work is done to overcome an opposing force. In other words, negative work corresponds to situations where an external force acts against the motion of an object, causing it to slow down or come to a stop. For instance, the frictional force acting on a moving train does negative work on the train. Negative work implies energy is being taken away from the system or is used to overcome resistance. Work, is it scalar or vector? If we apply 100 newtons of force on a cart and move it 5 meters to the right, we do 500 joules of work on it. If we apply 100 newtons of force on the same cart and move it 5 meters to the left, we still do 500 joules of work on it. It is just that the cart is displaced to the left instead of the right. So the total work done on the cart equals 500 joules plus 500 joules, which equals 1000 joules. Since the work done on the cart does not depend on the direction, work is a scalar quantity. Challenge questions. How much work is Valence doing on the grocery bag? Pause here and check your answer. Valence does 0 joules of work on the grocery bag because of the 90-degree angle between the force and the displacement. Is Ion doing work on the weights? Pause here and check your answer. Yes, Ion is doing work on the weights and her muscles. The force and the displacement are in the same direction. Is Isaac doing work on the boulder? Pause here and check your answer. No, the boulder has 0 displacement, so no work is done on the boulder. But Isaac is doing work on his muscles since they twitch in the direction of the applied force. Exo of mass 50 kilograms is doing push-ups. She raises her body by 30 centimeters during each push-up. How much work is she doing on her body with each push-up? Pause here and check your answer. W equals F times delta D. We are going to be using this formula to solve this problem. We see that Exo is moving her body against gravity. So force applied is basically her own body weight. So force equals 50 kilograms multiplied by 10 meter per second, which equals 500 newtons. The displacement delta D equals 30 centimeter, converting that to meters, which is equal to 0.3 meters. Work done on her body with each push-up equals 500 newtons times 0.3 meter, which equals 150 joules. So there you have it, the physics of work. Work, as we just learned, is a dynamic interplay between forces and displacement in various everyday actions. Now that you have learned about the physics of work, here is a solve it yourself question. How much work does Endo of mass 55 kilograms do on her body as she climbs a vertical distance of 100 meters? Happy learning! Thank you.